Hello. In this lecture, we will discuss NAT traversal. When one of the IK gateways or both of the IK gateways are behind a NAT device, this requires some changes. First reason why NAT poses an issue for IPsec is the fact that ASP packets cannot be network address translated. The ASP is a protocol in of itself and doesn't ride over TCP or UDP, and since the ASP packets are encrypted, NAT is not supported. So, to solve this issue, there was a couple of RFCs created to extend IPsec functionality to accommodate for this scenario. This was added as a vendor extension. Both sides of the connection need to support the NAT traversal extensions for this to work. So, in the first couple of messages, message 1 and message 2, the two sides advertise to each other the vendor IDs. They advertise NAT traversal as a vendor ID which enables this capability. So, the initiator sends the responder a vendor ID indicating that NAT traversal is supported. This is in message 1. The responder sends the initiator back a vendor ID indicating that it too support NAT traversal. This is message 2. So, those two messages need to be exchanged and both sides need to support NAT traversal for the next phases to take place. In messages 3 and message 4, the two sides exchange NAT discovery messages. Those messages will include a hash of the IK gateway interface's IP address and port used for IK. The actual IP addresses are not exchanged, just a hash of the IP address and port, which is port 500. If either of the side doesn't receive the hash it's expecting back from the other side, that means the other side is behind a NAT device. So, we will look at one example in this lecture. We have two IK gateways. The IK gateway on the right is behind a NAT device. The firewall on the right is NATing the IP address of 172.16.1.5 to the IK gateway IP of 10.1.1.2. The next steps are in messages 3 and message 4. In message 3, the initiator would collect its source IP and port and run it in a hash function. If the initiator has multiple interfaces, it will do the same for all interfaces and create a hash for each interface IP. It will also add the port in the hash. We will see why in a future lecture why the port is added to the hash. The hash function outcome will then be sent to the responder in message 3. Those are sent in the NAT discovery fields. The responder gets this NAT discovery message. It will run the hash on the initiator IP and port. If the received hash message does not match, that means the initiator is behind a NAT device. It will run its own source IP and port hash. In message 4, it will respond with its own hash. The initiator receives message 4. It compares the hash with the expected hash. If they don't match, that means the responder is behind a NAT device. So, let's review those two messages, message 3 and 4 again in more details. Step 3 is the initiator calculating its hash. The initiator will do what it normally does as part of this step, which is create its Diffie-Hellman key. This is step 4 in this diagram. It will send the NAT discovery hashes along with its Diffie-Hellman keys in message 3. The responder will receive the message. It will compare the hash with the hash value it's expecting back from the initiator. This is step 5. It is expecting a hash for the IP and port of 172.16.1.2. This matches the hash received from the initiator. This checks out. Now it does the Diffie-Hellman exchange, step 6. It calculates the master key, step 7. The responder calculates the hash of its source IP and port. This is step 8. It will send the hashes for its own source IP address and port and send it out in message 4. The initiator receives the message 4. It would extract the NAT discovery hashes. It knows that the IP address it sent to originally for this remote IKE gateway was 172.16.1.5, port 500. It calculates the hash for 172.16.1.5, port 500. This is step 9. It checks the hashes received from the responder to see if any of the hashes provided matches its own calculation. This is step 10. None of the hashes provided in the responder message 4 is matching. So, it determines that the remote IKE gateway, the responder, is behind a NAT device. This is step 11. The reason why is that the hash it's expecting back didn't turn out. Using the Diffie-Hellman keys, it will calculate the master key. This is step 12. It will calculate the master key and SKIDA, DNE. This is step 13. When it sends message 5, it switches to UDP port 4500. The responder would get that message on its UDP port 4500. So as part of the incoming packets processing, it checks the SPI and compare it against the Security Association database. It concludes that this is for an existing SPI session will switch to UDP encapsulation. So, based on it receiving the traffic on port 4500, it will respond to port 4500. From now on the communication would switch to UDP port 4500. The ESP packets would be encapsulated in UDP packets. So, when the two sides continue their communications during phase 2, they will be communicating over UDP port 4500. Let's take a look at the last two messages 5 and 6. It definitely helps for us to refresh what happens in those two messages. We know that the pre-shared key is determined based on the IP address of the remote IKE gateway. When the initiator look up the pre-shared key, it will locate that pre-shared key based on the IP address it originally sent the packet to, which in this case is the IP address 172.16.1.5. It will not actually know anything about the actual IP of the destination of 10.1.1.2. The initiator doesn't really know that IP address, it only knows that the hashes sent by the responder didn't match any of the values it's expecting. So, as it does in any main mode processing, it calculates the seed key. It will also calculate SKIDA, D, and E. This is step 15. It will then create the identification proof. It will hash it with the SKIDA, encrypt it with the SKIDE, and then send the encrypted hash to the responder. It will send out message 6, the last message. It will send that message out to the initiator on port 4500. This is step 17. The initiator would get message 6. It will decrypt it using the SKIDE. It will verify the hash. If it checks out, phase 1 is complete. Phase 2 quick modes messages will utilize that same UDP port 4500. The reason why I am going into those details is that we will go through more complicated scenarios that would require full understanding on how this process works. See you in the next lecture.